ready?
Yep, it's starting.
Hi, I'm Anodna,
And I'm Eric.
and we did our research survey on artificial intelligence in games. So we wanted to explore how we can combine existing approaches in the field to develop more effective and more efficient approaches to game solving. The significance of this area of research can be found in a lot of fields because games can be used to model many real-world situations. For example, training robots to complete a task, or coming up with an efficient algorithm to allocate resources. And therefore, this domino affects into applications in fields like military strategy, corporate analysis, business negotiations, and obviously robotics and gaming. There are two main camps of current approaches in the field of game solving. The first one is reinforcement learning approaches. So typically, researchers are currently developing actor-critic models because they're highly scalable and can be trained in parallel. The second approach is to use game theory. So this includes trying to approximate a Nash equilibrium for a game, or using game abstraction techniques for more efficient game solving, or using opponent modeling techniques to either emulate opponent behavior or exploit the opponent behavior. Some challenges that are facing these very same approaches include the very large action and state space of many games, making brute force solutions non-viable. A challenge facing reinforcement learning approaches is the long time horizon that some continuous time games have, therefore leading to sparse reward functions. And finally, a lot of current game AIs are targeted to solving specific games and therefore have non-generalizable heuristics. So while they may make breakthroughs in solving one game, they don't really help in solving future games. The first one we're going to explore is AlphaZero, which is one of the current state-of-the-art forms of AI. Its predecessor, AlphaGo, was famous as being the first AI to solve the game Go. And it managed to accomplish this using an insightful combination of Monte Carlo research and reinforcement learning techniques. So it began by using supervised learning on human data of human gameplay of the game Go, and it used this data to initialize the models. And it then used deep neural networks to train the policy and value networks of the reinforcement learning model. So then the output of the value functions could then be used as heuristics in the Monte Carlo research. So what that would look like is you start by training the two networks, the two policy networks and the value network, and then use the output of the value function as a heuristic at each node of the Monte Carlo research to make it more efficient. This was then further developed into AlphaZero, which is now the state of the art, and it managed to entirely remove the need for supervised learning on human data, and it now learns entirely through self-play, beginning with only knowledge of the game rules. This version of AlphaZero was able to generalize to solve chess and shogi as well as Go, and it combined the policy and value networks into a single neural network so that it could be more efficient to train, since you only now have one network to train, which it was able to do so in the span of 24 hours and then be able to successfully solve Go. An important note that we learned from AlphaZero was that while previously the state-of-the-art in chess solving AI had been Stockfish, which used an alpha-beta search approach to solving the game, AlphaZero was able to actually perform better than Stockfish using its Monte Carlo research approach, which this graph demonstrates by showing that it was more scalable to solving larger numbers of moves over time.
Cool. So the next AI we'll talk about is that of OpenAI 5, developed by the OpenAI company. So this AI is used to solve the game of Dota 2, which is a real-time strategy game played between two teams of 5 players in a zero-sum game. So currently, OpenAI 5 is considered the state-of-the-art in solving real-time games, which are different than the games we saw AlphaZero solve, which were sequential perfect information games. Real-time games, rather than being sequential and turn-based, are played continuously, so you can think of most computer games being a real-time game. Although OpenAI 5 has not yet solved Dota 2, as they have not yet beat professional Dota 2 teams, although they have defeated teams of ex-professionals. OpenAI 5 was trained using the PPO algorithm, which is a small modification on general actor-critic model reinforcement learning algorithms that are highly parallelizable and allows them to train the network with years of GPU and CPU hours very efficiently. Some techniques developed in order to train OpenAI 5 were a specialized reward function in order to mitigate the issue of having a sparse reward function in reinforcement learning. And also the technique of having this team spirit parameter, which allows the 5 different agents on a team to try to collectively maximize their collective reward function rather than maximizing their individual reward functions without explicitly communicating with each other. And the final AI I will talk about was that of Lebradas, which is developed here at CMU in order to solve heads-up no-limit poker. One interesting thing about this approach is that it took a very game-theoretic approach rather than a reinforcement learning approach in order to solve poker. So Lebradas developed some major breakthroughs in the field of solving imperfect information games. They started by using game abstraction in order to abstract the very large game of heads-up no-limit poker into a smaller, more reasonable game that they could then solve using this supercomputer using regret minimization techniques to pre-compute a Nash equilibrium strategy for this smaller version of the game that they then used as a blueprint strategy to solve poker. One of the major techniques developed in order for Lebradas to solve poker was that of subgame solving. So while they initially learned this strategy beforehand, at runtime, based on the current state of the game they were in, they could then perform subgame solving in order to further refine their strategy to exploit this current situation they found themselves in. This technique had not been seen before in any kinds of imperfect information solving AIs. Lebradas also employed opponent modeling and exploiting techniques in order to exploit whatever strategy its opponent was playing, and he used this in order to defeat poker professionals in a multi-day poker tournament. Finally, we'll talk about some future directions the field could take. So one is behavior cloning and opponent exploitation, similar to that as we saw in Lebradas, although Lebradas can only use that because it took a game theoretic approach. And it would be cool to see this generalized to any kind of reinforcement learning agent. And in general, we would like the field to produce generalized game agents that could solve any game and not just sequential or imperfect information games like those we've seen. Another approach is coordinating multiple game AI, so rather than just having one AI developing multiple agents that can coordinate together like we saw OpenAI 5 do with their team spirit parameter. Combining the search, intelligent searches like alpha beta search and Monte Carlo tree search with the intuition provided by neural nets like we saw AlphaZero do, although we're able to generalize that not just in sequential games but to any kind of game. And then finally, doing time abstraction in games. So this would mean turning real-time games like Dota 2 into abstract discrete time games that we could perform a search over, like Monte Carlo tree search.
Thank you.